What's up, everybody? This is Mr. Richardson coming at you live through the power of the internet. And what we're going to be talking about today is how do we multiply monomials or single algebraic terms? Well, in order to understand how we do that, we have to understand how we multiply exponents. Well, just so we have common language, we're going to refer to this piece of the exponent as the base and this part here as the exponent, meaning this is the piece that's doing repeated multiplication this many times. So for instance, if I wanted to evaluate these two, I could figure out the product of 2 squared and 2 cubed. Well, we know that 2 squared equals 4, 2 cubed equals 8, and when I multiply 4 by 8, I get 32. I could also evaluate 2 to the 5th and get 2 times 2 times 2 times 2 times 2 5 times. 2 times 2 is 4, times 2 is 8, times 2 again is 16, times 2 one final time is 32. You might be asking yourself, why are these two answers equivalent? Well, it's because they're actually the same thing. If you think about it, on the left-hand side, I could write 2 squared times 2 cubed, problem number 1, and on the right-hand side, I could write problem number 2, 2 to the 5th. Well, 2 squared is just 2 times 2, and 2 cubed is just 2 times 2 times 2, and 2 to the 5th is 2 times 2 times 2 times 2 times 2. That's a lot of 2's, but you can see that either way, 2 is being multiplied by itself 5 times. And that brings us to this really exciting rule for multiplying monomials, which says if you multiply two exponential terms with the same base, you can add the exponents. For instance, here, 2 squared times 2 to the 3rd, they have the same base. I can add the exponents 2 plus 3, and I'd get 5. We can use that to simplify exponentials. For instance, when I'm multiplying 2 to the 3rd, x to the 3rd times x to the 5th, because the bases are the same, I can just add the powers, and this simplifies to x to the 8th. Here I want to multiply these two monomials with the same base, and when you multiply two things with the same base, you can just add the powers. So this would say y to the 12th plus 9, which is y to the 21st power. And don't get confused by number 5. Just because these are not algebraic expressions and they're actually numbers, it still works the same. When I multiply things with the same base, I can keep the base and just add the powers. Here I'll add 6 plus 2 plus negative 3. 6 plus 2 is 8, minus 3 is 5, meaning here I get 3 to the 5th, which would be 243. This one I was able to simplify one step further because they were just numbers and not a variable to some power. Let's see if you can try one on your own. See if you can find the product of these two algebraic expressions. Well, product is really just a fancy way to say what is the answer to a multiplication problem, so I'll rewrite this as multiplication. Then when we multiply things with the same base, we can add the powers. 8 plus 2 is x to the 10th. Now this works great, but sometimes what happens is these algebraic terms have coefficients. When the algebraic terms have coefficients, what you still do is when you multiply things with the same base, you can see here we add the powers, but the coefficients aren't exponential terms, they're just regular numbers, so there we just multiply them. For instance, let's try these three examples. If I want to multiply these two terms, I notice that they have the same base. So when I multiply terms with the same base, add the powers, I'll add 3 and 5. But this 3 and 2 that are coefficients, I'm not going to add those because they're just regular numbers. I'll end up multiplying those. 3 times 2 is 6, 3 plus 5 is 8, and I get 6x to the 8th. Going to do the same thing in number 8. When you multiply terms with the same base, you add the powers. So here I can add 12 plus negative 9, and negative 5 and 2 aren't exponential terms, so I'll multiply them. Here I'll get negative 10 times y to the 3rd. Let's try one more. Here again, when you multiply things with the same base, add the powers. Here there's an imaginary coefficient of 1 in front of this a term, so I'll do 15 times 1 times a to the 2 plus 3, or 15a to the 5th. As you get better at these, this step here is really just taking place in your head. You're not going to actually write that on paper as you get better. As you start to do them now, though, if you feel like you need to do this in order to get the correct solution, by all means try that. Let's try one on your own. See if you can find this product. When we multiply terms with the same base, you add the powers. However, 7 and 4 are not bases of exponentials, so those actually get multiplied. So here I can write the product. I'll take 7 times 4 and add 3 plus 5, and I'll get 28x to the 8th. Let's try one more. See if you can find this product. Again, product just means a multiplication problem. When you multiply things with the same base, add the powers. This term of s here has an imaginary power of 1 since there's only one of them. Here, add the 2 and the 1. I'll get 3. Multiply 6 and negative 4. You'll get negative 24 s to the third. Now there's one more rule I want to leave you with, and that is what happens when you multiply things without the same base. We talked a lot about what happens when you multiply things with the same base. You add the powers, but what happens if the bases aren't the same? Well, if the bases are not the same, for instance, I multiply x to the mth times y to the nth power, I'm not going to add those exponents because the bases are different. You're only going to add the exponents if the bases are the same. For instance, if I was multiplying these two terms here, because x's were the same base, I could add their powers, m plus n, and the y's were the same bases, I could add q plus r for something like this. So if I look at example 12, I'm multiplying these two monomials, but what I notice is that the bases aren't the same. This one has a base of x, and this one has a base of y, so I will not add 3 and 2. What I can do, however, is still multiply the coefficients 3 times 2, and what I would get is 6x to the third, y to the ninth. Notice how these powers did not add together. When I look at number 13, I'm going to follow the same process. I'm only going to add the exponents for ones that have the same bases. So when I multiply x squared and x cubed, I can add 2 plus 3. And when I multiply y to the 5th times y to the 7th, I can add those and get y to the 12th. Should I add negative 5 and 2? What do you think? Well, the answer is no. These are just coefficients, so those get multiplied. So I'm going to multiply negative 5 times 2, get negative 10. Add the powers for the like bases. 2 plus 3 is 5. 5 plus 7 is 12. And I get a final answer of negative 10, x to the 5th, y to the 12th. Let's try one more. In number 14, what I want to do is multiply these two expressions. I only add the exponents for the ones that have the same bases. Here I have a coefficient of 3 and a coefficient of 1. I could multiply those and get 3, and I'll add these exponents of 2 and 3. That will leave us with 3 a to the 5th times b. Let's see if you can try one on your own. See if you can find this product. Here what we have to do is multiply the coefficients, negative 3 times 5, and only add the exponents for the like bases. Here, this x has an imaginary 1 as an exponent, so I can add 1 and 2. And when I multiply y squared times y cubed, I can add the 2 and the 3. It should look like this. I'll get negative 15, x to the third, y to the 5th. Again, this step here is really taking place in your head. If you want to get used to writing it now to get comfortable with this method, that's fine. But later on, you're going to skip right from here directly to the solution. Let's try 2 more before we get you out of here. See if you can find this product. Again, multiply the coefficients. 3 times 6 is 18. Add the exponents of the like bases. Here there's an imaginary 1. I'll get x to the 4th, y to the 6th. Final problem. See if you can take this product. Here, multiply the coefficients. 4 times 2 is 8. Add the exponents. There's an imaginary 1 here for the x term. 2 plus 1 is 3. Add the imaginary 1 here with the 3 there, and I get y to the 4th. Thanks so much for tuning into my video. I hope you really learned today how to multiply monomial terms. Until next time.